Hello, everyone, and welcome to this 9th lecture of this lecture series, 40 under 40, the last one before the summer holidays. And we have a pleasure to finish in style with the Professor Abdulla Ghani from TU Berlin. I will introduce him a little bit, and then we'll leave him the floor. So Abdulla Ghani graduated from TU Berlin with a diploma in aeronautical engineering. And during his studies, he worked as a student for Siemens Energy in Berlin, Airbus in Toulouse, and DLR and Lufthansa in Hamburg. In 2012, he started his PhD thesis at Fairfax in Toulouse on LES of combustion instabilities in aeronautical gas turbines. And after completing his PhD, he worked as postdoc at the Institut de Mécanique des Fluides de Toulouse for 1 year, and followed by a 3-year postdoctoral fellowship at TU Munich. Since April 2020, he is appointed the junior professor at TU Berlin, with directing the chair of data analysis and modeling of turbulent flows. His research portfolio includes analysis of experimental data, high-fidelity numerical simulations, reduced order, and data-driven modeling techniques. Besides scientific collaboration with industry, his research is funded by an ERC starting grant since 2022. So it's good to have you here, and please, I leave you the virtual floor.
Thank you very much for this very nice introduction. Thanks for the invitation, for giving me the opportunity to present here some work. I just give me a second to, prepare. All right. All right, so hello everyone. Thank you for being here. Thank you for taking the time before your holidays, participating today here. I am really excited actually to speak here and to show our work from our group, the Data Analysis and Modeling of Turbulent Flows group. So it's in short DMF. And I want to start with a quote that I just recently found. And it was extremely exciting actually, to read this. So combustion is the oldest technology of mankind. It has been used for more than 1 million years. I thought about this lately a lot, and was kind of, thinking about combustion used by early man 1 million years ago. So this is not just a claim or something. This is, scientifically proven that there were fireplaces in the past where people got together, they cooked their food, they had social, interaction and conversations, perhaps, I don't know. And, this is kind of, the transition of being a human or an animal. If you cook your food, this is kind of a definition I would set at this stage here. So really exciting actually to think about that. And then thinking about the technology, that combustion is a technology. The people, the early humans at that time thought about, they researched perhaps in their ways and their, abilities, how to put this fireplace, where to put it, how to control the fire. So this was something I was recently thinking a lot about actually. So very interesting topic, I would say. But coming back to technology, I don't have to specify in this community of combustion people that combustion is super important actually, and it's kind of driving a lot of technologies that we use in our daily lives, either directly or indirectly. So all of these things can happen. And what's common in all of these applications basically is that whenever you want to use a flame, technically, what you do is you put this flame inside of some kind of a chamber. And this is where we talk about combustor design. And combustor design is not something that you can just, do. Perhaps you can, but not in a very efficient way. So you have this tension triangle, let's say, where you have this trade-off always between emissions, stability, efficiency. So you cannot build a combustor which is just efficient without taking into account stability or emissions. You cannot build a combustor which is just having super low emissions, but not look into efficiency or stability. So there's this trade-off that we have to look at. It's a multi-objective task, actually. And today in my talk, I will just focus on stability. In particular, I will talk about thermoacoustic instabilities. There are my main research during the past, since I entered research actually. And the objective of my talk is here to give an overview of methods for the non-experts, perhaps, of thermoacoustics in this field, so that you have an idea what is happening, how are methods used. And at the same time, for the experts, I would like to give an update what happened in our group, perhaps in particular, showing some newest results and some findings that we had. First of all, I want to start with it's like exemplifying what combustion instabilities, thermoacoustic instabilities look like. So you have here a mid-cut plane of a swirl stabilized flame. Flow is coming from left to right. On the top video, you see stable combustion, and on the bottom image or video, you see unstable combustion. So it's the same geometry, the same bulk velocity, just a little difference in the equivalence ratio. And at the end, this is the result that you have. So, very different flow field, very different fluctuations that you see here. And these fluctuations have an impact on the flame, of course. And this is something very general. So it's not only this aeronautical combustor where you use a spray flame. It's also seen, for example, in gas turbine applications where you have perfectly premixed flames. You can have that in annular combustion chambers where multiple flames interact with each other, but you can also have that in non-swirling conditions, like on the right bottom video, where we have a flame stabilized behind a bluff body. So in all of these configurations, these instabilities can happen. And then, they result in these large oscillations of the flame, which are, unnormal. And in these computations here, all of these CFD, modeling approaches show that the combustor walls are perfectly rigid, right? Nothing's happening. In real life, this is not the case. And what's happening is this. So this is a very famous picture now. So on the left, you have a combustion chamber before combustion operation. On the right, you have a combustion chamber after combustion operation. And during this operation, combustion instabilities or thermoacoustic instabilities appeared. And this is what happened. I mean, your combustion chamber is damaged, right? You cannot use this anymore. So thermoacoustics are a highly undesired problem. And we want to, understand why they appear and then get rid of them. Or even, understand and then get rid of them. Which brings me actually to the problem that we have here. So it's a mixture of unsteady heat release, which is, fluctuations of the flame. They're always there. And these unsteady flame motions generate some acoustic waves. These acoustic waves can interact with your fluid dynamics field. And then this, again, can perturb your flame. So you have this inherent coupling. And this is not just, a hand-wavy explanation or something. You can really derive this by using Navier-Stokes equations. You can derive the acoustic energy equation. And basically what it says is that on the left-hand side, you have the acoustics of your system. And on the right-hand side, you have a source term. And this source term is showing that if you have the product of pressure fluctuations and heat release rate fluctuations, and if there's at specific conditions, these two can interact, and the energy of the flame is going to be released or going to be transferred to the acoustic field of your system, which means that pressure fluctuations can grow in time and then lead to these large fluctuations that we have seen in the videos, or destroy your combustor if you're unlucky. So this is something that is known for a long while, and it's a really complicated problem. Why? Because I showed already we are dealing here with a multi-objective problem. We're dealing here with a multi-physics problem because it's not only combustion science, acoustics, and fluid dynamics that interact with each other. All of these aspects or specific fields bring their specific timescales and spatial scales. This is why this problem is really complex. And today, we have just few methods to analyze these instabilities, which I'm going to point out right now. So the first one is the brute force approach. This is, the most simple thing you can do. You can call it trial and error approach if you want. You design your combustor, you build it, and then you test. Then you find out, it's by surprise, if your combustion chamber is stable or not. If you're unlucky, then you see, this plot here on the right, where you see that at the beginning, your pressure fluctuations are kind of low, but with time and very rapidly, these instabilities grow, and you have these large pressure fluctuations appearing here as a limit cycle. The next, way to analyze combustion stabilities is by using the forced flames method, or computing the flame transfer function if you want, where we're using very specific waves, acoustic waves that we inject into the domain. So it can be experimentally or numerically. And then we compare these two, the signal of the flame with the signal that we have injected, and try to find out what this means. And I'm going to detail that now in a minute. So before showing this one, I want to just briefly say that, you know, there's a nice video on YouTube from École Centrale in Paris. You have the link there on top. What they have done is they have built this kind of a very simple flame. It's a Bunsen flame, and they used specific sound to force the flame to get into motion. And what we will see is that there will be 3 different tones. And for each of these tones, the flame surface, which you see here, will react differently. So just pay attention to that. I hope it was audible and you could hear it. So we have seen 3 different frequencies, 150 hertz, 200 hertz, 300 hertz, and each time the flame surface was reacting differently. This is the approach that we want to use, actually, to use this forced flame approach, or to compute the flame transfer function. So what's the flame transfer function? If I recapitulate again, so we have acoustic waves, they enter the domain, they excite the flame. So the heat release rate fluctuations, I can integrate that over the domain here. And then I have 2 signals which, you know, evolve in time. I'm using here very low velocity fluctuations to stay in a linear regime, and so that these signals are harmonic. So you see that there are smooth sinusoidal waves. The white one is the velocity fluctuation, and this bluish one are the heat release rate fluctuations. And now we see that these 2 signals can be linked to each other by 2 parameters, let's say. So first of all, there's one physical thing where you inject the velocity perturbations. It takes a little while, and then the flame responds. And this you can see, for example, by comparing the peaks here of the velocity and the peak of the heat release rate fluctuations. So it's first the velocity and then the heat release rate fluctuation responding to the excitation. The second point is that we're not only having some differences in time, but also some differences in amplitude. So the amplitude that we have injected here for the flame, which let's say it's, you know, a number, and then the flame responds at the number half of this number. So, you know, you have 2 different parameters now with which we could evaluate now the response of the flame. Let's say this was 100 hertz signal, and then we evaluate this 100 hertz, the flame response of the system at 100 hertz by a gain, which is, you know, the difference in amplitude, and the time delay, which is kind of the phase between these 2 signals. And this you can plot into a Bodo diagram. And this is what you have, right? We have evaluated now 1 single frequency. Perhaps this is, you know, an experiment, something easy to do, but for a numerical simulation now, if you want to access the entire frequency range, let's say from 0 to 800 hertz, you have to repeat this procedure 800 times to get this kind of information. Then we talk about the flame transfer function. Well, to be strict, that's the flame frequency response, but that's another topic. So we have now this flame transfer function, and we see that, you know, computationally, this is expensive. For an experiment, this is not the most expensive part, to do a frequency loop to get this flame transfer function. And we have now, I will present in a minute or explain this image here. So there is a work methodology based on these flame transfer functions, which are, you know, the key element that you need for thermoacoustic analysis to understand if your combustion system will be unstable or stable. So it's a prediction tool. And to highlight and to go through this with you, I picked up an experiment from my thesis. This was an experiment, so it's not me who did the experiments. It's an experiment which was run by the honorer at that time in Toulouse. So you don't see here on the left the injection tubes. It looks like this part here. So these are the outlet tubes. This is at the beginning, you have the inlet tubes. Here, this section shows the combustion chamber. And here, you know, you have the flame image in a zoomed window. And I will launch the video in a second, but please pay attention that during time or with time, this combustion chamber length, the outlet tube length will be increased. This is indicated by this blue arrow. So with increase of this outlet tube, the stability of the system will change, and you will hear, like in the middle of the video, that there is a switch in the sound that you hear. Well, that's it. So that's a combustion experiment. It uses a spray flame. It's a swirl configuration in an academic environment, atmospheric pressures, instability frequency at 200 hertz roughly. And my job at that time was to replicate this numerically and to use numerical simulations to reproduce the same stability map, let's say, from stable to unstable. So step 0, of course, for these kind of computations, like validating your computations and against experiments. This can be either in a qualitative way, like here on the left, or in a more quantitative way, where we compare mean flow field profiles in the 3 directions, X, Y, Z. And now we start looking into the work process of the thermoacoustic analysis. So on top here, we're in this mode where we say we have low velocity fluctuations. We inject them into the computational domain, excite the flame at specific frequencies. In this case, it was 200 hertz. And then we measure the heat release rate fluctuations. So in this paper, especially, I've used a bit of a different method to obtain the fields. But in general, the idea is the same, like I explained before. You have 2 signals, U prime, Q prime. You compare these 2 by having a gain and a time delay or a phase. And then you inject these information now into the second part of this work methodology, which is the acoustic solver here. And note that, the computational domain, I go back, the computational domain was only this year. I neglected the inlet tube and the outlet tube that I showed in the video. But in this acoustic world of using some acoustic solver, in this case, it's an Helmholtz solver, it's possible actually to generate the entire system by just solving for the acoustics of this system. So on the top, you see the small configuration. On the bottom, you see the large configuration. And plugging in your flame transfer function into your inhomogeneous Helmholtz equation now and computing the eigenvalues, you see that for the short configuration, we had a prediction of stable combustion. And for the long configuration, it was showing that the combustion chamber will be unstable, which is, good news. It's successfully showing that this method works. So it's not me who invented this entire workflow, but I was one of the guys who used that. And in the paper, we also, just as a side note, show how you can use, one single mesh, one single configuration, and do this transitional steps between the short configuration and the long configuration. So if you're interested, go and check out the paper. So, the point that I want to make at this stage is here, we have a workflow, it's working nicely, but it's restricted to only one single frequency if we just want to pay the price for one single computation, right? So the flow field of the LES will change, of course, if we change the operating condition. And perhaps the same operating condition would react differently if we excite this flame with another frequency. So there are a lot of questions that are basically not solved just because we look at one single frequency. And the restriction for this is, again, we cannot do a sweep in frequency by using LES. It will take ages, right? So, and this is now the question that came up a few years ago. And the group of Professor Polivke in Munich, they established really this method called CFD system identification, so in short CFD/SI. And what they do is they use techniques from control theory, namely it's system identification, where they relate input fluctuations to output fluctuations. So I will just go through that briefly, but I recommend, if you're interested in that, go to these reviews that Wolfgang Polivke has written. So what happens here is that we don't use a U prime signal that we generate as a post-processing step, which contains one single frequency, but instead we're generating something which has multiple frequencies. So it's a broadband signal. It's containing a range of frequencies. That's why this signal is not looking anymore like a single sinus wave, but it contains some multiple frequencies, and then it's looking like this. This is the input signal. We put it again in our CFD computation, but the trick is now we only do this CFD computation once. And this is the point which is drastically reducing the amount of computation. We inject this broadband frequency, retrieve a heat release rate signal, which looks like this. And then with the system identification techniques, it's possible to correlate these two signals and find out what the flame transfer function is. So, if you just recall what I just said before, the single frequency approach is giving you, the gain in time, gain in phase for one single frequency. But since we have now system identification techniques, you can actually forget about that and go for the system identification technique and obtain this yellow curve now, where you have the information of the frequency range for the flame transfer function with one single computation. So this is super powerful. So this is the one here. So the main bottom line here is one single computation, and you have the entire flame transfer function. And once we have this kind of a method, we can, analyze physics with that, because this is methods, and with methods, we try to understand physics. So here in the paper, for example, from 2021, we investigated the impact of a pure methane flame. You inject hydrogen gradually from 0%, 10%, 20% to 50% of the fuel mass fraction. And then you obtain that the flame transfer function has very specific shifts only due to the hydrogen injection. And in another step, my student Mario Kasel, he could analyze with these techniques what's the impact if we merge now, hydrogen injection and we go higher in pressure. Can we balance some effects, cancel out some effects? How is the flame transfer function looking like? Is this something that we could have guessed from previous FTFs? Yes or no? So if you're interested in these kind of physical knowledge on flame transfer functions on generic flames, I recommend going to these papers and having a look into it. So with these methods, computational techniques become now tools to study physics, which is super important. I've shown now this workflow that it's kind of robust. It's working quite nicely, even for these turbulent cases using swirl flames, for example. But this is restricted only to the linear regime. This is what I just said, because you need low velocity fluctuations to inject into this domain. Now, some situations you're interested in the nonlinear regime because you want to know, for example, the amplitude of your limit cycle happening in your combustion chamber. Then you need to go for a higher amplitude forcing, because we know that the flame is not only changing with the flame response is not only changing with the sweep and frequency, it will also change with the sweep and amplitude. So this is very important to know. But there's one specific question now, because I just said system identification is coming from control engineering, and it's restricted to linear systems. Basically, it assumes that your system is a linear time invariant system. And once we talk about nonlinearity, you're not anymore linear, right? So we know that system identification for the nonlinear flame regime is not working. And what are now the different methods that we could use to assess from the CFD point of view these kind of nonlinear flame dynamics? Of course, the frequency by frequency approach would work. So this is also something that is done classically in experiments, but they don't have this problem in time series generation. But for the numerical people, this is really a problem. And again, the group of Wolfgang Polivke worked on this. They used very early in 2017, actually, neural networks to mimic the response of the flame, or to learn actually the response of the flame, so that they can assess the nonlinear regime of the flame, because machine learning techniques are very well suited for nonlinear modeling. So what they have shown also in a follow-up paper in 2021 was that it is possible to mimic the nonlinear, or to reproduce the nonlinear frame response with one single computation, but the length of this computation is super long. So for this simple laminar flame here, the computational time, DNS is referring here to flame resolved DNS, so the chemistry is still simplified, which is kind of a typical thing we do in thermoacoustics. So the computational time here was 1 second, which is, you do it just once. You cannot do that, in a design phase or for a turbulent flame, because then you would need more than 1 second even. So this was, sparking the idea in our group. Okay, what other methods are available that we could use to reduce this long time series requirement for learning? And case A here, so you see we have a table here. This is the y-axis is denoting the time. Case A indicates the case where we use 1 second of simulation data to train and validate the neural network. And then based on the work of the group of Polivke, we build up with case B, C, and D and try to minimize the amount of data. So only the yellow part of the graphs here is used. So we reduce the data length by 50%, so that we just use half of a second, a quarter of a second, an eighth of a second to reduce more and more to see what is the lower limit in modeling the flame response using these kind of machine learning techniques. And what we have found out is that we're not using a standard feed-forward neural network. We're using a type of recurrent neural networks, which is made for the sequential data sets. And we train this model now with the reduced data sets, like half of a second, a quarter, an eighth. And then we extrapolate, we just run this model and see what is the latest time series looking like. So this is from 0.9 to 1. This is this bluish curve, and then plotted here again from 0.9 to 1.0. And we see that the ground truth, so the DNS that we really computed, is well replicated by model A, B, C, and D, which is really nice. It's indicating the extrapolation ability actually in this case for flame dynamics modeling. And then based on these time series, we could evaluate what's the flame transfer function now. And we compared it with our ground truth, which is the frequency by frequency method, to be really sure that we're computing something correctly. And what we see here is the flame transfer function for an amplitude, inlet amplitude, velocity amplitude of 50%. So before it was 5 to 7% to stay in the linear regime. And now we're talking about 50% of the mean flow, which is highly nonlinear. And we see that all of these models, no matter with which time series lengths we're dealing here, they replicate these yellow diamonds which come from the CFD. And what is really surprising, and the highlight of the work that Vikas has presented in Vancouver last year, is that with this one single computation, we trained the LSTM model. And this trained model is now able to reproduce the flame dynamics for all the amplitudes which are below 50%. So no need to rerun any DNS anymore. So this is what we have done. We've taken the same model that we have used here. We now inject some velocity perturbations in the linear regime, and then retrieve the same flame transfer function that was determined experimentally by these yellow circles, which is quite cool. And I don't show it here in the paper. No, I don't show it here in the presentation, but it is in the paper, sorry. All the amplitudes in between, so below 50%, like 40%, 30%, 20%, 10%, 5%, all of the information is inside of this model with this once trained model, which is really, really cool, because it says that once we have this model now, you run one single DNS, you have access to the entire linear and nonlinear regime up to the amplitude that you have injected to train your model, which is really cool. In this paper also, we indicate how you can implement pieces of, theoretical knowledge, so physics that we know from frame transfer functions, to reduce even more this computational time. So if you're interested in that, please have a look. So I give just an intermediate intermediate summary here. So there is a robust workflow to study thermoacoustic instabilities experimentally, numerically, but especially for the numerical people, computational cost is the restricting point. And generating time signals is directly correlated with time signals generation, with computational time, sorry. So now we have seen there are methods which give us access to the linear and the nonlinear frame regime, which is really nice. And we've seen that these data-driven techniques allow us actually to reduce the heavy computational cost and just open the way to extend these system identification methods that we had, which were limited to linear systems. I hope no one is sleeping at this stage. So I just want to, change a bit the perspective now and going away from this computational, from the CFD heavy perspective, and just think about for a second what data means in our engineering science. Because when we read or hear about machine learning, a lot of people tell you, yeah, okay, data is there, right? Just take it and then you can use it. And a lot of people, you know, are happy with that. That's fine. But in our specific cases, especially in combustion applications, you know, it's not that straightforward that you have tons of data that are available. And one enabler for machine learning, especially in engineering, are sensor techniques. This is something that I barely hear actually, but it's super important to mention that, you know, there was a transition from the sensor techniques during the last years, where these sensors became now digital. So they have wireless connections. Sensors can be, you know, one sensor can measure multiple things at the same time. This is really exciting, I think. There are sensors which are super small. So you can really, this miniaturization aspect, you can, you know, they're super small and you can place them now everywhere. They're robust. So in the World Cup 2022, sensors were placed into the football so that, you know, they could track really where is the position of this ball. Is this a goal? Yes or no? You know, in critical cases. So these things are really robust now, and they're smart because, you know, they use different abilities that are available today. And at the same time, there are also sensors which have their own actuation systems, which is also kind of a benefit. In our field of combustion, and in particular, I'm talking here about gas turbines, sensors are always used. So from Werner Krebs, for example, I know that in a Siemens gas turbine, there are around 6,000 sensors. Of course, there are not 6,000 pressure sensors, but at least you have some of them. And these are used to track the health of your engine during time. So then you see with time, you know, some pressure signals or temperature profiles, whatever, are deviating from some kind of, you know, means that they had beforehand. And then you can indicate which kind of maintenance procedure you have to take to you know, do an overhaul or something. So what's the link with combustion stabilities? We're using pressure signals actually to, you know, see, okay, there are pressure fluctuations. You do an FFT of that, you obtain a frequency, and, you know, in some cases you put them in some advanced methods, and then you say, well, I really see that this is a closed loop, so we're talking about the limit cycle. So in my opinion, this is, you know, just the beginning of using this data. There's perhaps a lot more to discover. And another thing that we also use, and in labs especially, I guess, so you have one pressure sensor, and then you have access to the frequency and the amplitude and time. And then I plot this here. So X is the length of this, you know, generic combustion chamber, and the pressure fluctuation amplitude is here on this axis. Now I put a second pressure sensor, and I see, okay, frequency is the same, but the amplitude decreases. And then I put another one, and then I see, okay, I have now 3 pressure sensors, 3 different amplitudes. So I have an idea which kind of acoustic mode is perhaps active in this chamber. This is something that is used, for example, to identify what mode shapes look like. So these sensors are available in gas turbines or in combustion systems that are, you know, so what's the link with flame transfer function, you might say, because I want to talk about thermoacoustics. So think about the situation where you cannot obtain the flame transfer function. Let's say you don't have a loudspeaker to excite your flame. So the only thing you have is perhaps an unstable combustion chamber. You have your limit cycle signal, which means that, you know, the flow naturally excited the flame. And this is, you know, an information that we could perhaps use. So this was the sparking idea when I first started working in this direction. And if you recall the work flow that I just showed before, so one super important element is the flame transfer function, and the next important element is an acoustic solver. Before I showed a Helmholtz solver, which is, you know, 3D solver, and now I'm talking about a 1D solver, which is basically the same if you consider one-dimensional acoustics. But the nice thing is that this combination, flame transfer function and an acoustic solver, gives you access to the frequency of instability, to the growth rate, so if it's damped or if it's amplified, and it gives you information of the amplitude at a specific location. Now, if you recall that the pressure sensor data that we have, they are located at very distinct positions. They don't change in position in time, right? And you get an information about the amplitude. And from this pressure signals, we're also able to compute a frequency. So what we can then think about is turning this workflow and saying that, well, the acoustic network model is basically for free because it's just based on the geometry of your system. It's not including any fluid mechanical or combustion processes. So it's just volumes. This you can build always, actually. You have your measured data from your real experiment. You know the frequency and you know the, depending on the number of your systems, of your sensors, sorry, you know the pressure amplitude at these distinct locations. So then as an inverse problem, perhaps we can find out what's the flame model that is, fulfilling this kind of setting here. So this was the basic idea that started in this direction. And in 2020, during COVID ASME online presentation, I gave a talk on this here. If you're interested in the paper, you find it, of course. We show that this method of reversing the flow and using pressure time series to obtain a flame model is working for a Ricci tube, for a laminar flame, and also for a turbulent flame up to 7 or 10 bar. I don't remember anymore. This was an experiment that was performed by Isaac Box at that time at DLR in Stuttgart and with Kerry Norrin together, where we use pressure information to exactly identify the flame model. But I'm not going to detail here how this model works, but there was one limitation here, and the limitation was the same limitation that we have seen just before. Since your combustor is just stable or unstable at one specific frequency, you only have access to one flame response, so only one gain and one phase at one specific frequency. And just put here 100 hertz to recall you like the image that we've seen before. So what will be interesting now would be to have those dashed curves where we find out the entire flame transfer function over the entire range, just based on the same pressure time series that we have seen before. And this was work that was presented last year at the ASME in Rotterdam, and it's available online. If you're interested in that, I would be happy if you look into it, because I just give a glimpse of what happened. So the work that we have presented there is this blue frame here, and it's using different models. So you use a parametric model for a flame model, which has 6 different parameters, and there are ways to eliminate some of these parameters. There are ways to use analytical approaches to estimate some of these parameters, and we can give some kind of a constraint to these parameterized flame transfer function models by giving the information that we have for this one specific frequency, which is the work of 2020. All of this together, cooks up this new model. No, not cooks up, it cooks this new model. And we've applied it to a turbulent flame. It's a perfectly premixed methane air flame, which was investigated by Thomas Komarek, mainly, I think, in 2010, in the group of Wolfgang Polivke. And the nice thing is that they had different operating conditions, and they measured for the same operating conditions stable configurations. So they determined the flame transfer functions, but they also changed the combustion chamber length to have an unstable combustion, and then recorded the pressure time series. So we have access to both the flame transfer function for validation and the pressure time series as an input for the approach. And then there's one specific point. So we have 2 different swirler locations. So they change the swirler from the front position, denoted by F, in one experimental campaign, and in the other one, they put it on the rear position, which was denoted then by R. And the 2 power ratings that they had were 30 kilowatts and 70 kilowatts. And this is, the flame transfer functions that they have measured are the circles from the experiments, and the line, the white line here, is the estimation of the model, just putting pressure time series recorded from the experiments and rebuilding in one-dimensional in one-dimensional acoustic network model the cavities and the system actually as a geometry. That's it. You put these 2 things together, you let this machinery work, and then at least, of course, you don't have a 100% agreement, because this is not feasible with something which is just estimating. So it's just giving you a good idea of what's happening. So the flame transfer function here is quite close to the real experiments. Also for the 70 kilowatts, it's not really bad. The most challenging one was this one here, the rear swirler position at 30 kilowatts. Even for these parametric models that we have actually used as a basis for this approach, even for them, this is a challenging configuration here. So it's not really surprising that it's not working super well, but it works. At least it gives you an indication of how this flame transfer function would look like, because instead you would have no guess what the flame transfer function would be. Yeah, and the cost of this is just 1 hour on a standard work machine. It's just an optimization procedure that you let run. So I'm coming now to the end. So if you forget everything what I said today, just take home 3 points with you. Thermoacoustics are an important topic, especially today when we talk about hydrogen, when we talk about climate change and reducing emissions. The second point is that machine learning has the ability to give new paths, new ways to model things. So this is something that is really nice and exciting. And for us, or for me in particular as a CFD guy, this is opening ways to go with reduced computational times, especially because I have to have a time series. And as a general remark, we in engineering can rethink how we can use old data in a new way and to find creative ways to make use of these things in a perhaps different way than it was before. To conclude, so I want to thank my group. So I have an amazing group of super motivated guys. So it's Mario, Vikas, Paul, Maria, Shazid, and Florian. 3 other people will join at the end of this year. So 3 different faces, maybe in the next presentation. And we're working on different topics, ranging from flame wall interactions, flashback, machine learning modeling, physics from neural network, whatnot. And if you're interested in that, just check out our webpage. Maybe not today, I have to update some things, but on Monday at least. And then you can find some information. If you have further questions, you're interested in anything, just write an email, and then I think I'd be happy to reply. Thanks a lot.
Thank you. Thank you for this very nice presentation. Now it's time for questions. So if everyone from the audience has a question, please feel free to raise your hand or unmute yourself and ask a question.
Thank you for the presentation. I have a sort of a peripheral question. You mentioned about the sensor, you talked about the data. And so we run all these experiments in order to find the stable operating range for these combustors. But when a thermoacoustic instability happens, it can be either a bad design or it can be an external excitation. And so I was just wondering that if it is an external excitation, which could be an issue with, let's say, the fuel line, and there could be a fluctuation in that, or it could be an issue with the flow line. And in that case, even when we look at the combustion systems that are there in the industry, they rely on solid dampers or passive methods to kind of dampen those instabilities. But now with the models that you talked about, we can predict, prevent, or if we don't prevent, we can actually dampen it before they reach to the limit cycle. And so my question is that, how efficient is it to have a control system that rely on data that is collected using the sensors that you mentioned about in real time, and then actually modulate flow or fuel in order to prevent or at least dampen such an instability? So that's question one. And the second is, if it is possible to have an active control over there, what would be a preferred way to do that, to control it by modulating flow or to control it by modulating fuel? Because one gives you a handle on fluid dynamics, but the other one gives you a handle on, let's say, the chemistry that is going on in there, but also to an extent on fluid dynamics as well.
Well, there is no, so I'm, as a scientific guy, I'm not going to extrapolate. So I just say things that I really know and for sure. So I don't know what is the best method. Active control was something that, for example, was used in the 1990s. If you check some old papers from École Centrale, among others, and you see that, active control is working. It is using dynamically the data that you're recording. But there was this, the certification problem that was hindering it to use it on a daily basis. Coming to your second question, if it's better to modulate the flow or modulate the flame line, well, it depends. I mean, I haven't done these kind of studies. It depends heavily on your configuration, on how the shape of your flame transfer function is, what the acoustic modes are. So there's, a number of things that you have to know before tuning that. So there is no general rule of thumb that you could just give.
No, thank you.
Okay, we have two more questions from the audience. So I will ask first Jimmy John to ask his question.
Hello. So yeah, thank you for the presentation. Very nice. So my question is about your latter method that you showed. Would you expect it to be applicable for whichever type of fuel? Let's say pure hydrogen versus methane. Would you expect changes?
It depends, because the parametric flame model, that's the basis, right? I mean, these are exchangeable bricks if you want. So if you have a parametric flame model for purely hydrogen flames, then you can just replace that, because we use the parametric flame model that was built for methane in particular. But this is easy to do, to evaluate that, and you just change that, and then you can run your tests. I mean, I don't see any limitations a priori for the type of fuel.
Okay, perfect. Thanks.
Okay, we have a question from Matteo also.
Hi.
So,
Thank you for the presentation. I would like your point of view if it's possible to use like rather lower fidelity approaches with respect to LES to model this kind of phenomenon, to construct the flame transfer function like RANS, or even lower than that, because I guess the computational cost is very high to run simulation like this.
Yeah, I mean, this is, kind of an old question, right? I mean, if you think at the beginning of CFD, it started with RANS, where people wanted to address the flame transfer function using RANS. This exists already. If you look at ACME papers from 2010, 2005, something like that, you'll find these kind of works. Sure, it is applicable. It is working somehow, perhaps, or even not, but it has its restrictions, because no lunch for free. So you cut some of the physics, and then you lose somehow the quality of your prediction.
Yeah. Thank you.
okay, we have one more question from Balasundaram. I hope that I pronounce your name correctly. Please. If you can unmute yourself.
I think I'm audible now.
Yep.
Yeah.
Thanks for the nice talk. Actually, I need a clarification regarding this flame transfer measurement when you force with the broadband noise. So we calculate how do you understand the flame dynamics, like when you do excite with the broadband forcing? So because when you do a single frequency forcing, so you will be able to see how the flame moves over an instability cycle, right? So how do you do the similar thing when you do excite with the broadband forcing? So that's my question. First question.
So it's not anymore the same approach. So you're using different tools. If you use the single frequency method, at least so you use FFTs to compute the phase and the amplitude. But if you use system identification, then you have to go for the system identification tools that are explained in this review paper of Wolfgang Polivka, and use these methods. So it's not anymore.
I think I'm not clear, I guess. So can we see the flame surface movement? That's what my question is. When you excite with the broadband forcing, so for a single frequency.
What was that? Flame surface moment?
Yeah. So the flame oscillation. So the heat release rate. How will you?
Okay.
Can you filter out and see or something like that,
well, so from my understanding, right? I mean, you have a
Yes.
flame, you give one single frequency, and then you
Yes.
see this one single frequency on the flame surface.
Yes.
Let's say it's a laminar flame. Now you inject multiple frequencies, then of course on the flame surface you see multiple things happening. That's it.
Okay, okay. So I have one more question in slide number 25. Actually, I need a clarification. So what is the reference location you take when you measure this flame transfer function for this such a complicated burner you have?
Sorry, what was that?
The reference location so you use when you calculate this flame transfer function in slide number 25.
Which slide you said?
25.
This was given by LDA, so it was just shortly after the dump, so right after the swirler.
Okay. And then how do you introduce this forcing? That's also I would like to know. So
numerically or experimentally?
I mean numerically. So where do you introduce actually?
At the inlet of the combustion of the computational domain, which is, you know, at the moment where this conversion part is going to start. I mean, you have the details in the paper, but there I explain everything.
Okay, okay. Yeah, I think that's, thank you so much.
Okay, good. We have one more question from Guillaume. If you can unmute yourself and ask your first name.
Salut, Guillaume.
We cannot hear you. Sorry, Guillaume. No, we cannot hear you. So if you write the questions on the chat, maybe that would be a solution. In the meantime, I was wondering if these methods can be applied also when you have sort of hysteresis phenomenon while changing, I don't know, operating conditions. Sometimes you have a flame shape transition and hysteresis happening. So yeah, I was wondering if there's the applicability of the methods that you have shown.
Yeah, so I haven't tested that, but you know, just from a guess, I would say whenever you have a flame shape transition, or if it changes, the flame transfer function also changes. So then, if the method is capable, and if the flame transfer function changes, this means the way the flame is receiving the amplitudes of the velocity fluctuation will change, and this will translate somehow in your pressure time series, for example. So I would say, why not? Yeah.
Okay, thank you. So it's just recomputing the flame transfer function with based on the data, based on the pressure time series that.
Yeah, and perhaps adopt a model, because here I'm just showing a model for swirling flames. But if you're talking about, Bunsen flames or something else, then you have to switch this model.
Okay. Thank you. Okay, we see that Guillermo can make the microphone work. We can try the chat. Okay.
Yeah, go for an email.
Okay. Are there any more questions from the audience? We had already a very
maybe last one. You have shown the promise in generalization capabilities of these machine learning approaches. How do you see this going in your field, in perspective, or in general in the combustion field? What is your take on the use of machine learning techniques, their abilities to generalize and also to include physics knowledge?
Yeah. So this
is your opinion on that. Thanks.
Yeah, sure. So this is something that is really interesting for me. So we're currently working on that, to put as much as physics into our neural networks, because I think as a perspective, just going for purely data-driven machine learning, like neural networks or something, it's not going to do the job, especially when you extrapolate. So whenever we have some kind of information of physics, we have to include that. So this is my opinion, and this is what we are working on, actually.
Thanks a lot.
Sure.
I let Salvatore conclude.
Yes, I think I think it's time to close the Q&A session and to conclude this event. And let's thank again the speaker for his very nice presentation and this very nice Q&A session. And yeah, I'll like to remind everyone that you will find the recording on this lecture on our YouTube channel, or the Belgian Section YouTube channel. So subscribe and follow us, and we all see each other in September, most likely. So enjoy the rest of your summer and holidays. So thank you everyone for attending this lecture, and yeah, have a good summer. See you soon. And yeah, thank you, Abdulla, again for the nice talk.
Thanks again for the organizers. Bye-bye.
Bye-bye. Have a nice weekend.